We're here today because we want to talk about developing and testing ETL pipelines with no risk against production-like data. That's the reason that we're here today. Just a few a few rules for everybody to be aware of, or regulations. I don't know. This is actually streams on two platforms. Some of us are here on Zoom, and I think we have some people also on LinkedIn. You're all anonymous. There are options to ask questions either on the comments in LinkedIn. Those of you who are connected on LinkedIn, or there is a Q&A here as well. You're more than welcome to click on the Q&A and ask questions in the Q&A over here. If you ask a question, then I think that's actually, you have the option to ask it anonymously. You have an option to not. So if not, just be aware of that as well. I'm going to be here in the Zoom, and my colleague is on LinkedIn, also monitoring the questions there. I'll also ask questions here, and you'll have the opportunity to answer them either here or on the Zoom. As mentioned, I'm here with lakeFS, and we're going to talk today about developing and testing ETL pipelines. I apologize that I'm starting straight out of the gate with a question, but would love to kind of understand if there's folks here that are familiar or not familiar with lakeFS, and who are we talking to today? Just so I'll know how deeply I should go, how much in depth I should go and describe lakeFS versus not, and then I'll just talk about like the Python integration and the ETL capabilities and things like that. So okay, so I'm starting to get the answers. Okay, and I don't know if I don't know if we are getting answers from LinkedIn or not, but if so, I'll ask my colleague to write those for me. If not, then that's okay. So from what I see, most of the folks here today are not familiar with lakeFS, so only we have a few that are somewhat familiar with the process. So I'll assume that there is very minimal understanding of what lakeFS does. Okay, and we'll take it from there. So why are we here? Why do we want to talk about testing ETL pipelines? Because obviously it's important, right? Thanks everybody that answered. Because obviously it's important to test, especially in the world of big data. And there is a big difference between unit testing and actual testing at scale, especially when you come to big data, when the size of the data makes a difference, the type of the data makes a difference. And you know, this thing on the right here actually happened to me once, right? And we're here today to talk about that. And kind of the mode of operation today for all of our users that we speak with is as follow. I want to develop a new ETL pipeline. Everything that has to do with the code is very easy. You typically use GitHub. You have the ability to take your code, create a branch, work in isolation, and continue on. But when it comes to creating a data environment to develop and test against, that's actually very complicated. And what people actually do is they usually create their own buckets, and then they either sample data into their bucket or copy data into their bucket. And then they take their ETLs and they point it to that private bucket, and then they experiment with multiple runs, run the ETL, change something, do this again, run the ETL, change something. There's a lot of alt tabs going on when we actually go and do this. And when we're done, we take the code that we just wrote, we point it into production, and we hope that everything's going to work in production. By the way, this takes time to the point that sometimes it takes too much time, and then we have to resample the data. This is not the only way. There are other ways. You're more than welcome to share those in the Q&A or in the comments. Some people do things such as copying data. Some people separate readers and writers. So you'll read from one bucket and you'll write to another. There is this manual dance that everybody does that tries to generate an environment that we can test against. So that's kind of the world that we operate today. We have to develop a new ETL. We do our best to create the best environment that we can to develop against data and to test it. It's a manual heavy lifting process that's also not great, because if I copy data, then it's expensive and it's time consuming. If I sample data, it's just not good enough of a data set to test against. There comes lakeFS. lakeFS is a solution that we build that helps you manage data as code. It's something that you can spin up really quickly in 20 minutes. We're actually going to do it, I think, in even less throughout this webinar. And what it does is it sits on top of the object store and it provides a Git interface on top of an object store. So imagine that you can take a bucket and you can branch it. And you can make changes to that branch and you can commit changes. If you're unhappy with them, you can revert them or you can roll back. If you are happy, you can merge changes. So I can actually commit and merge from one bucket to another. And then the ecosystem of tools that we have in our environment can access the data through a lakeFS API. And from a refactoring perspective, it's actually super easy. If before we were accessing a collection on a bucket, now we will include a name of a branch or a commit identifier. A name of a branch would be prod, test, dev, e.test1, e.test2, e.test3, any like an issue number. You can have millions of branches in your environment, just like we're familiar from Git. Or a commit identifier will be production yesterday at 5 p.m. before an ETL ran, or production yesterday at 10 p.m. after an ETL finished. Or, for example, the data set that I used for testing a specific ETL at a specific point in time, right? So that's like a snapshot, a commit, right? A commit identifier or a branch are two ways that we can access different versions of our data. Nothing here is new. These are all concepts that we're all familiar with from Git, but it works at big data scale. And then where will I run these Git actions, right? Where will I create a branch? Where will I merge? Where will I commit? I can run those from a web UI interface. I can run those from a command line interface. We have a lakeCTL command. I can run those from operators within a DAG, an Airflow DAG, for example, or I can run them directly from within a notebook using Python code, which is kind of the part of what we're going to talk about today. We have a Python client where I can, for example, create a branch and use and work against an individual branch directly from my notebook using Python. I'll pause here, see if there's any questions. If not, I will continue. Awesome. So how does this work? And I think this is where it starts being very interesting. Like we said, lakeFS works for data lakes that run on top of object storage. So I have here a bucket. And by the way, this bucket can be anywhere. It can be an AWS S3, it can be an Azure Blob, it can be a Google Cloud Storage, but it can also be an on-premises object store. So a MinIO, a DailyCS, and NetApp Storage Grid, right? There's hundreds out there right now. Any object store whatsoever. And the data with lakeFS, any version of lakeFS, will always sit in place. So you have a bucket here and you have a bunch of files here, objects, right, on your object storage. And the format doesn't matter. It can be an iceberg table, a delta table, a Parquet file, a CSV, images, annotation, anything that you want. And then every commit in lakeFS is a collection of pointers to objects that sit on top of that managed bucket. I see a question: how many different repositories should one create? Whether it is mapped to one database schema or one repo can have multiple databases. We have not yet discussed repositories in lakeFS, and I'll show that soon in the demo. But a repository in lakeFS is a logical term, and it's your decision whether a repository should be a collection of data sets that work together, which is kind of the common case, or it's just one data set, or it's your entire data lake altogether. But going back to how lakeFS works, as we said, we have here a managed bucket, and we have files on top of that bucket in any format, images, videos, Parquet files, iceberg tables, and so on. And every commit in lakeFS is the collection of pointers to those objects. Now, object stores are immutable, right? Meaning if I want to go and edit this file, then I'm actually going to create a new version of this file, and we do copy on write. So when a new file is created, the next commit will point to that additional file. But files that did not change, like this file over here, you will have multiple commits pointing to the same physical object, physical file. Why is this so powerful? Because imagine that now I want to create a testing environment. I want to create a copy of my data. Okay? That will be a metadata-only operation. I'm not actually copying anything, just pointing to the same files, which means that A, this is super performant, right? We have thousands of users that we are aware of, right? Some of them run hundreds of petabytes of data lakes. This will always take milliseconds because I'm not actually copying anything. And the second advantage is that exactly that, I'm not actually copying anything, right? There's tremendous amount of storage saves associated with this. A lot of times when data lakes today are being addressed, like you go into a data lake and you see like never delete one, testing two. There's a big mess. There's a lot of copies of the same data. There's multiple instances that and there's no deduplication basically, because a lot of folks, and this could be data engineers and this could be data scientists that are all working on their individual experiments, and there is tremendous amount of storage savings, both in multiple environments, right? I can have here millions of branches. Every data engineer, every data scientist can have their own copy of the data without actually copying the data. And the second dimension is actually the time dimension, because by nature in data lakes, a lot of times you have a big chunk of the files of the data that repeats, that is static. And then you have a smaller subset of the data that is added and removed on a regular basis. And you can go back in time this way without the need to take snapshots of the same files over and over again, because we actually deduplicate the object store over time. So that's how lakeFS works, right? The first use case, which is the use case that we're speaking about today, is exactly the use case of creating dev test environments. And by the way, this doesn't necessarily need to be take my production and create a test dev environment directly out of my production, although it can be, right? But even if you have reasons to completely separate production and dev test, imagine that you have a single testing environment, and then you can multiply that for every person, every test, every ETL, every branch, and so on. And then the other use cases that you will use this is for things like creating CI/CD pipelines for your data, right? When we actually go and we create the merge of the data, we'll run some automatic tests like schema changes, or making sure there's none of those, or that you have some quality checks that you want to run, that you want to make sure that there's no PII data in places where the PII data shouldn't be, and so on. And of course, if something bad happens, we can always roll back. We can always take the data sets and roll back. And the cost of an error becomes really milliseconds, as opposed to today, which is, it's a very time-consuming, heavy labor effort to kind of go and recover from bad data that's in production in a data lake specifically. And the last use case worth mentioning is machine learning reproducibility, right? We mentioned that we can access data in specific commits, meaning that you can now version control the data sets that were used to train your different models. And you can compare those, and you can train a new model on the old data set or the old model on the new data set, and compare those. And just in general, you have the lineage and the auditing of finding out and being able to understand what was the raw data set that you used and how you modified it to train your model, and so on and so forth. But we're going to focus now about developing ETL pipelines with lakeFS, as we said before. And instead of that long process that we had before, we're now going to have a much shorter process. We're going to take our data set, we're going to branch it. I create a copy of this data, then we're going to develop against this branch. And at the end, if we want to, we can actually merge the changes back into prod. So this becomes a much shorter process, a much less dangerous process. I can write a retention ETL that will delete data if I wanted to support GDPR or for any reason that I delete data. And I can do that without actually risking deleting the wrong data or deleting production data and developing this and things like that. It becomes a much more safe way to do this, following our engineering best practices that we're familiar with from code. How are we going to do that? And this goes to the technical part of our demo today. We're going to use a lakeFS sample, and we're going to do this start to finish now. We're going to use a lakeFS sample. We're going to clone it. We're going to run lakeFS and the min.io object store and a Jupyter notebook and Spark, and we're going to run everything together and show you how that is done. I see another question. Okay, let's see how this looks. Okay, no, not a question, sorry, just a comment. Okay, fantastic. But if there are questions, then please feel free to reach out. So let's go and look at that. Actually, let's go back and look at that prerequisite. So I'm gonna get out of here. Okay, fantastic. And we're going to go into our samples. So you have here a link. You have also the link over here. This is our samples repository. So the lakeFS samples repository has a lot of samples. Okay, all you need is a Docker in order to run this. It has a lot of samples. What I'm going to do, actually, I ran this before, but I'm actually going to, I want to show you this from the very start. So I'm going to stop the samples. I'm going to copy everything. I'm going to walk you through the entire thing that I'm expecting you to be able to do to show you what this looks like, really start to finish with no problems. I'm going to delete the samples that I have right now. And I'm going to go to my terminal. And I'm actually going to really, you know what? Let me really delete this. lakeFS samples. So our journey starts with us cloning this repository. So I'm going to clone the samples repository and I'm going to go to it. So here we go. And as this is copying, I'll use the time to walk you through what this is. So these samples repositories have a lot of different samples. You can go to the notebooks and see those. And the idea here is that there's two ways to run this. If you run this just with a Docker Compose up, then it will spin up a Jupyter notebook that has Spark. It has the notebooks, and you can run those against any lakeFS installation. That can be the open source lakeFS, that can be lakeFS Cloud, it can be anything that you want. However, if you don't have anything running and you just want to start running with this, then there's also a profile called local lakeFS. So you can run lakeFS with this local lakeFS profile, and that will spin up not only the Jupyter notebook, but also an object store. In our case, this is min.io, and it will also spin up lakeFS. So you have a full environment with the lakeFS Git for data solution, with the object store, and with the Jupyter notebook all together that you can play with. And that is done by, again, cloning this repository and then running Docker with the local lakeFS app repository. There's a question. What if you have multiple environments like dev, QA, stage, and production? Can we have lakeFS repo mapped to each environment in which it's linked in a different AWS S3 bucket in different environment? Or the approach would be to have just two environments and main production? That's a great question. It's so great that it's actually, we have one of those samples here. So when I go and when I bring up these samples, I'll show you one of the samples that literally answers exactly that question. If I want to physically separate prod, test, dev, stage, and how will lakeFS work on that? So I'll show you what that looks like as well. We have a sample here, not a sample that we're going to go through right now, but we have a sample that goes through this example as well. So let's see, how is our terminal going? Yeah, everything is up and running. Everything was cloned. Now, this token compose command will probably be pretty quick on my computer because I've obviously run this before many times, but for you, when you run it for the first time, there's likely going to be some dependencies that you're going to need. But that's it. Everything is up and running. I'll show you what I have here. I have the MinIO UI. So if anybody wants to go and look at the object store, you can look at the object store this side. Okay, here's my object store. MinIO. I have here my Jupyter notebook. Here's my Jupyter notebook, and the index here gives you the list of all the notebooks that we have here in the samples. And I have here my lakeFS UI, including, notice that you have here the access key and the secret key that you have to use this lakeFS interface. So, like we said, oh, sorry for that extra zoom. We have Jupyter, MinIO, and lakeFS. MinIO, Jupyter, lakeFS. Just a side comment for the question that was sent before. In this demo, we're going to talk about integration of lakeFS with Spark and Python. The question that was asked, version control of multi-bucket pipelines, is an example of prod, QA, and dev separate environments and still achieving lineage and so on and so forth. We also, I'm pretty sure we have a webinar recording on this as well. I'll say this at the end. We also have a super responsive Slack community. So if I don't get to the actual recording during here, feel free to join our Slack, ask the question. I can point you. I'm on that Slack. There's the help channel there is super effective as well, and happy to send you to the right place. The recording of this demo. That's literally the question that you asked. But for the more basic use cases for folks that are joining today, we're going to talk about integrating lakeFS with Spark and Python. Today, that's the demo that we're going to use. And I think the nice thing about this is that we can really just go line by line and see what this looks like. And I think you saw we spun up this entire environment in just a few minutes, and we have everything up and running. It's a great way to get familiar with lakeFS. So the first thing that I'm going to do here is I'm going to point this into my lakeFS. So we're using this prepackaged lakeFS sample. So all the default that are used here are the ones that we can use. However, if you're using, for example, a lakeFS cloud environment because you want to benefit from some other things, then you want to basically insert your lakeFS endpoint here and your credentials over here as well. So we'll start with that. The next thing that I'm going to configure is a namespace. A namespace is the path in which a repository will sit on. Okay, pause here for a second. So we saw lakeFS. lakeFS has different repository. This is a repository like Quick Start. A repository is a logical term. This was asked before, so I'll call this out again. It can be a group of data sets that work together. It can be your entire data lake. It's completely up to you. Every repository has a path that it sits on, like a storage path that it sits on, that in our case, we're configured to sit on top of MinIO, and I'm going to put my repository on top of this example bucket, I think. Yeah, this example bucket. And now, and this will be the name of my repository, Spark Demo. Now I'm going to create the client so I can use Python code. By the way, we actually have a wrapper client that's even easier than what you see here in this demo. We recently being like 2 days ago, we released it officially and put all the documentation around it. So in the future, whoever is looking at this recording, there's actually probably even easier code that you can use to do this, and we'll change these as we go. And then I'm going to create a repository, and this means that if I go here to my lakeFS, I see here a new repository called Spark Demo. Okay, so here's the new repository, Spark Demo. And I'm going to start a Spark session. And the last things that I'm going to do here is I'm going to give some namings. So what will be the name of my branch? What will be of my production branch, of a new branch that I'm going to create, and path where my data sets are and where my files are. And this is a super simple environment, just like a single CSV that we're going to use. Now, the next thing that I'm going to do is I'm going to upload a file to my repository. I'll pause here for a second because this is important also. There are two ways to introduce data into lakeFS. One is by uploading and one is by import. There are questions I see in the Slack. Other than creating object repository, what is the main advantage of lakeFS? How is it different from others' repos? So the main advantage of lakeFS is that lakeFS provides version control on top of data at big data scale, right? So for example, the ability to create multiple testing environments and then data lakes is not possible without lakeFS, which is the branching and the commits and so that we're going to see here in a minute, just to answer the question on LinkedIn. Okay, fantastic. Thanks for sharing that. There are two ways to introduce data into lakeFS. Okay, I see also an open question on LinkedIn. What are the features that we get in lakeFS from security and governance point of view? I'll answer that. How well does this integrate with Delta tables? Okay, these are two very, very important questions, and I will answer them. I have even a slide to talk about them, but I'm going to pause them for a second, and I'll talk them after I continue here with the flow. I love all the questions. Keep bringing them up. I'm gonna pause in a minute and answer your question, Nikunj. Just we'll get there. We'll get there. Okay. So I have a repository, Spark demo. Okay, and I want to introduce files into this repository. There's two ways to do this: either by uploading files or importing files. Uploading files is exactly what you think, right? I can go and I can upload the file, right? And importing files is going and pointing to a bucket somewhere else, and then just creating these pointers that we spoke about, right? So not actually copying the files, but only creating the pointers to those files. In this case, I will go and I will upload the file. So now if I go to my repository, I should see a new file, lakeFS test.csv. This is literally just 5-column CSV file. These changes, once I uploaded this file, just like Git, are uncommitted changes. I can review all my uncommitted changes. I can commit those changes. In this case, this was pretty straightforward. We uploaded the file, so I'm just going to go ahead and I'm going to commit these changes. Okay. Now, there was another question in LinkedIn, so I'll answer, because I think this is a good time. Is lakeFS similar to Project Nessie for iceberg tables, but more generic? lakeFS, I think the closest thing in terminology to lakeFS is Project Nessie. Project Nessie is also a Git for data solution. It runs only on top of iceberg tables, and it's also limited in the way that it runs on top of iceberg tables. We give a more broad solution even on iceberg. I think that's why some of the world's largest iceberg users actually end up using, even though they use iceberg, end up using lakeFS for version control. Yeah, it is, but the obvious statement that you made here in the question is also correct. lakeFS is not limited only to iceberg format, or it works with any open table format, including Delta tables, which I'm going to discuss how it integrates with extremely well later, or not, or Parquet files, or unstructured data, right? Like images, videos, a lot of things of that nature. So that's a great question, and thanks you for asking. The next thing that I'm going to configure here in my demo is the ability to access the data. I'm going to configure an S3A gateway. There are two ways to work with lakeFS. One is with an S3A gateway, and the second one is through a lakeFS client. We're going to use the gateway here. And here now, what I'm going to do is I'm just going to look at the branches I have and the commits that I have in them. So I have, as we know, I have a single branch, right? My main branch, we created a single commit where we added this CSV file into this branch. Now, for some reason whatsoever, I want to create a copy of my file. For example, because I want to develop an ETL against it with no risk, right? I can do that by creating a branch. I can go to the UI and create a branch directly from here, clicking at create branch. By the way, I can create branch not only from any other branch, but from any other commit in any other branch. So those of you here that have some data ops mindset, you can start going wild with things like late arriving data, backfilling, reprocessing, troubleshooting, historical things. Like there is a lot of really complicated data tasks that become super simple if I can just go, oh, let's look at the data set holistically as it was yesterday before I ran the ETL, and just rerun the ETL and then rebase the solution, for example, right? But in our case, again, this is the very simple example. We're just going to create a branch out of main. Again, I'll do this using my code. So here I'm creating a new branch, right? If I go and I read the data from my new branch, then I'll obviously get that. Well, actually, what I did here is I repartitioned the data in my new branch, right? In this case. So now I have my main branch has my original data set, and I had my experiment branch where I just repartitioned the CSV file and I have some new data sets here. In other words, I run an ETL against my experiment 01 branch. It changed it only on my experiment, but it did not change anything on my main branch. Okay, so now I can commit these changes in my experiment branch, and I can see the differences between those two branches. By the way, the differences, again, I can see that now that I have, right now I have two branches that are no longer pointing to the same commit identifier, right? Because I took main, I branched out, I made some changes, and I commit those. So they're on different commits. So I can also compare those. I can see what's the difference between experiment 1 and main. We can see that experiment 1 has these new partitioned data sets. Okay, I want to pause before I continue on because there's a lot of questions out there. So let me make sure I answer those questions. So first question was, what are the features that we get? Actually, the first question that I will answer is, how well does it integrate with Delta tables? So there's actually a really strong integration between lakeFS and Delta tables. I will say that lakeFS is format agnostic, right? We mentioned this before. So you can run lakeFS together with Delta or with Iceberg. Now, and there is a difference in the approach between any open table formats. This is not only Delta and lakeFS in the use cases, and I'll just call those out here because those are important. One is, and by the way, these are two separate solutions. So I'm not saying lakeFS is better than Delta or Iceberg because I think that's comparing apples and trucks, right? I am saying that it's different use cases and different solutions that work very well together. What we do better is when you take the commit approach as opposed to the changelog approach, then what you commit is multiple tables together, right? So when I go to a different commit, I can see all the changes that happened across multiple tables. So if we take the Git approach, I don't want to go file by file and see all the changes that change in every individual, all the changes that change in every individual file. Instead, what I'm interested in looking at is actually the changes across the repository. That's different. The first difference. The second difference is the isolation. So exactly what we're talking about here, right? Being able to create multiple instances of our environment and working on them in isolation. And by the way, other open table formats like Iceberg also have branching, but not like these. Those are read-only short-lived branches. These are long-lived, read-write, full copies of the data branches that you can work on, right? And the third difference is specifically the CI/CD aspect that we spoke of. Imagine that just like code, before you go and you promote code, before you go and you promote data, you can run a hook automatic test, right? So make sure that my schema didn't change, that PI data isn't sitting the way that it shouldn't, or integrate with a data quality solution and make sure that the data looks good, and only if it does, promote this data, right? Because data quality solutions there's some incredible solutions out there, but all of them have a challenge that it's kind of like too early, too late, right? Either I found out that there's an issue in my staging environment, or I found out that I have an issue in my production environment after the data is already there, right? So integrating that with the CI/CD pipeline for your data means that never happens. So that's in terms of the added value on top of data lakes, but on top of data tables. But I will say even more importantly, where we are right now in the demo, you might notice that if you use lakeFS for data tables, you'll actually see the delta changes as well. So if you have, right now we're looking at the differences between two branches, and we see this on the file level. If you had delta tables here, then you'll actually see the differences on the tables themselves. And the last thing that I will say about this long-winded answer is that this is yet another demo that you have here. So there's a bunch of delta tables, delta lakes examples that you can use here to see that in action in your environment as well. So I think I answered the delta tables question. Another question that we have on the LinkedIn side is, can lakeFS be used as table catalog, or do I still need, I guess, an SE Hive, Unity, or whatever catalog I'm currently using? We have a lakeFS catalog specifically to support Iceberg, but we integrate with catalogs. We integrate with Unity, with Hive, so you can continue using the things that you're using. We have an integration with Unity as well, and it uses delta sharing as well. Just to answer the other question, I apologize that I'm kind of running over a lot of questions that were here. You say it's a zero copy solution. When we create a branch, make some changes and commit that, but does not merge them. These changes remain on the new branch that was created, so that data gets stored anywhere. Curious because we can have fantastic question. Okay, there's a question here about data management in general. Okay, and yes, many of the lakeFS users will end up with thousands, I think even more, of branches in their environment. And then they can commit changes in those branches, and they might not commit changes in their branches, and they might merge the data, and they might not merge the data. So let's look at this. I'll repeat the question that was asked and the Q&A in a different way. Okay, so we talked about this situation where you have some data sets, and then someone deletes a file or writes a new file, and then the next commit to point to that additional file. But there's a question of what happens to this file, right? And imagine that there's not one of them, there are literally millions of these, right? Temporary files that exist here that you need to work on and things like that. So lakeFS also has a garbage collection process, which is very advanced, right? It's repository specific and it's branch aware. And the reason that's so powerful is because you can really just declare the reproducibility that you're interested in. And you can say, for my production data set, for a specific branch, for my main branch, I want to be able to go 3 years back in time. So I want to keep this for 3 years, and then after 3 years, you can delete this. But for all my working branches, all those branches where I branch out, run some experiment, and then some data I keep, some data I don't keep, and I merge those changes, I want to be able to go 3 days or a week or not at all back. And then the lakeFS garbage collection process will go and take care of all these files for you. I have, if anybody's interested in a follow-up, I'm not going to go here I'm looking at the time, sorry. I'm not going to go here in more details, but there's a lot of more things that we can learn about this garbage collection. It's super powerful. It's also in the context of the delta tables, because someone asked about this also. It's also, I think, more effective than things like vacuuming, because when you vacuum, you lose the ability to go back in time altogether. And here it's very granular, and it gives you the ability to kind of to go through that in more details, right? I want to be able, this data set, I want to be able to go 5 days, and this branch and this data set, I want to be able to go a year, right? Things like that. So I think I answered that as well. Okay, what we're a little bit over the time. There is another question about governance, so I'll answer that in a minute. I think that's the last question that I have open here. If not, feel free to ask to repeat questions if I miss them. Sorry, there were a lot, and I really appreciate everybody's attention and question and participations. So last thing I want to show you, back to lakeFS. We have 2 branches, my experiment branch and my main branch. I experimented with my data. I made whatever change that I want to do. The last thing that I can do now is, look, if this is something that I just did for testing and I'm not interested in it, I can just delete this experiment branch. It will go away. As I mentioned before, the garbage collection will actually take care of any additional files that were created here that I don't need. This will all be taken care of for you. However, kind of the second use case that we didn't speak about today is actually atomically merging all these changes. So imagine this was a multi-table ETL that changed different things, and it didn't fail, and it didn't expose any of the data back into prod. But now I'm happy with it, and I want to promote these changes. I can do that by comparing these changes and merging them, or I can do that again. Once again, let's go back to our sample repo. You can see what are the differences between these 2 branches, and I can merge those changes. So I'm merging the new branch into my source branch, right? And here I can see those changes now. Okay. Now when I go to main, I see this new partition data. Okay, so I took the changes that I made in experiment and I merged them into main. And the cool thing about this is, again, the cost of an error is very, very small, right? So if something bad happened, I can just roll back the changes if I needed to as well. So so now I'm going to main, and look, I just rolled back the changes, and I can see all these changes, right? I can see where I added my first file, and then the changes that I made, and then how I merged those changes into main, and then how I reverted those mergers. And I'm saying that because this is where I answered the last question that I think I still have open, which is about security and governance. Okay, everything that you do in lakeFS is audited. Now, everything that we saw today is a part of the open source solution of lakeFS, right? So we have an open source solution, which is an open core approach, meaning there's no artificial limitations. You can use this on petabytes of lakes with no problem whatsoever. And we also have some additional governance capabilities using lakeFS. For example, you have using the enterprise features of lakeFS, which are available either in lakeFS Cloud, which is our hosted lakeFS solution, or in lakeFS Enterprise, which is lakeFS with those enterprise features that you will run on-premise on your environment. Remember, by the way, that even if you run lakeFS Cloud, the data sits on place by you, and we don't actually host the data, and we need very minimal permission. We don't even need permissions to read and write the data. Everything will done. We just need to know which data sits where. Excuse me, guys. Now, those things are role-based access control and single sign-on. So, and auditing as well. So imagine that when you use lakeFS specifically lakeFS Cloud and lakeFS Enterprise, then you can see for all these changes, for every commit, you can see exactly who did those with an integration, with an SSO integration, right? The actual user on your side that actually committed the changes when and where. And by the way, this is pretty powerful because also every file, similar to Git, you have a blame functionality. You can see where did this file come from, and then see the commit identifier that this file came from, and who changed it when. And I can go to the parent commit either, i.e., what did the file look like? What did the data lake, look like before I changed something? And this can be integrated with Git. So you'll see also the code that was ran. There is a lot of auditing capabilities available as a part of this, but also with lakeFS Cloud, you will get also RBAC capabilities. So you can say specific users can only read from specific branch, can only read from specific repo, can only write to specific area. You can protect your main branch and say nobody can branch protection, just like it. Nobody can change this file, but you can also merge into this, and that gives you a lot of compliance capabilities in place, and additionally more governance. So there is a lot of governance capabilities that we get that we take for granted for code just by applying these same engineering best practices to data as well. So I think I answered all the open questions. I believe so anyway. The last thing that I'll leave you with is some next steps. Please join our Slack. We have a very, very responsive Slack community. The help channel is very helpful there. You have access to the samples that we saw here today. You can spin up a lakeFS server using lakeFS Cloud if you wanted to. And again, we're blessed with a very big community of users. Would love to encourage anybody on this call to join our Slack, join the community. I'm there. My teammates are there. Feel free to ask questions. I'll pause here for a minute because we have a lot of folks online here still, and see if there's anybody that has additional questions or comments. See? Okay, going once, going twice. Okay, thank you, everybody. It was really, oh, wait, one more question. Okay, no more questions. Okay. I'll wait a little bit and I'll stop this. Thank you, everybody, for joining, and special thank you for all the many questions that we had across the different channels. There's a question, does it incur extra cost of managing metadata? No. The cost is not, there's no extra costs for managing metadata. What about scalability? Oh, that's a great question. So yeah, lakeFS was designed from the ground up, work very big data scale. I mean, you can look at some of the data sets that are here. So look, the scalability of there's a question, can I 10 petabyte to upload? Remember, like the scalability that you get on the storage level is from S3 or Azure Blob or Google Storage, from the object store itself, right? So we benefit out of the scalability that the object store gives you. We have multiple users that run bigger than 10 petabytes data lakes. If anybody's interested, then we also have in our on our docs over here, some benchmarks that we used that you can look at, and you'll see like we got like random reads and writes on I can't remember how big this was, in a 7.5 petabyte environment, less than, I can't remember, it was there's really good benchmarks here that you can go into. Oh, here we go. 99.9 under 50 milliseconds, 50% under 10 milliseconds of request. And there's also, Lake's ETL command line. There's also a command that you can use to abuse lakeFS. So if you want to try that, you can do that on your own, also in your environment. How can end user benefit from it? We mainly work with SQL users with Trino. Yeah, we have, absolutely, we have a Trino integration, right? We have many users using this with Trino. I think actually one of the samples that I have, let me check, I'm not sure. I think I have a standalone example with Trino. Yeah, AWS Glue Trino sample, if anybody's interested in this one as well. So this is yet another example that someone can use. And the way that end users will benefit from it is exactly like, imagine that you can get your own version of the data that you can experiment with as much as you want, and that we keep a change log, that we can develop against isolated environments, that we can make sure that when we change something, it's valid, that we can roll back in case of errors. All those use cases that we spoke about today, you can achieve those with your environment as well. Does lakeFS have integration with data catalog solution? Yeah, we have some integrations with data catalog solutions. Again, if you go to our docs, you'll be able to look at integrations, and there's a nice list over here. And if you have specific ones that you use and you'd like us to integrate with, please feel free to use our Slack. I'm not the expert to talk about every integration that we have out there, so I apologize. But on our Slack, you will get a really good answer for that question specifically. Okay, either some specific to integrate Data Hub catalog, or is it just S3? The integration is on top of S3, but I think that we have a catalog export capability. Would love to talk with you in more details about that. I think I'm not the expert, but I can get the experts to talk to you specific about ingesting Data Hub catalogs. Okay, I believe this is it. We also, I see we lost some of our folks. Thank you very much, everybody. Have a wonderful day.